Let us study Ellingham diagram. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. Such diagrams help us in predicting the feasibility of thermal reduction of an ore. The criterion of feasibility is that at a given temperature, Gibbs energy of the reaction must be negative. Ellingham diagram normally consists of plots of delta GF naught versus T for formation of oxides of elements, that is, for the reaction. 2xm solid plus O2 gas reacts to give 2mxO solid. In this reaction, the gaseous amount, hence molecular randomness, is decreasing from left to right due to the consumption of gases, leading to a negative value of delta S, which changes the sign of the second term in equation. Subsequently, delta G shifts towards higher side despite rising T. Normally, delta G decreases, that is, goes to the lower side with increasing temperature. The result is positive slope in the curve for most of the reaction shown above for the formation of MXO solid. Each plot is a straight line except when some change in phase, solid, liquid or liquid gas takes place. The temperature at which such change occurs is indicated by an increase in the slope on positive side. For example, in the ZNO plot, the melting is indicated by an abrupt change in the curve. There is a point in the curve below which delta G is negative, so MXO is stable. Above this point, MXO will decompose on its own. In an Ellingham diagram, the plots of delta G not for oxidation and therefore reduction of the corresponding species of common metals and some reducing agents are given. The values of delta GF naught, etc. for formation of oxides at different temperatures are depicted, which make the interpretation easy. Similar diagrams are also constructed for sulfides and halides, and it becomes clear why reduction of MXS is difficult. There are delta GF of MXS is not compensated. Let us study the limitations of Ellingham diagram. The graph simply indicates whether a reaction is possible or not, that is, the tendency of reduction with a reducing agent is indicated. This is so because it is based only on the thermodynamic concepts. It does not say about the kinetics of the reduction process. The interpretation of delta G naught is based on K. Delta G naught equals to minus RTLNK. Thus, it is presumed that the reactants and products are in equilibrium. That is not always true because the reactant or product may be solid. This curve is known as the Ellingham diagram. It shows the values for Gibbs free energy versus temperature for formation of some oxides.